Welcome to this special edition of Frequency Matters, the RF and Microwave Update Series. I'm Pat Hindle. I'm here with my co-host Gary LaRude and special guest Sean Darcy, Director of A&D at Analog Devices. Welcome, Sean.
Hey, thank you guys. Appreciate you having me on.
So Sean, there are numerous major changes going on in the space industry over the past 5 years, with the commercial sector playing a bigger role now, and there's a lot of deployments that are ramping up. Which ones are impacting the semiconductor industry and ADI the most?
It's a good question. So I think, I see three major changes probably in the space market that have been hitting the semiconductor industry over the past 5 years, probably continue for the next 5 years. The first is, space customers want to get the existing generation of technology on orbit. Historically, due to screening, things like lineage and qualification, satellites utilize components that were a couple of generations or sometimes many generations behind the terrestrial market. Second, the time it takes from inception to launch for most on-orbit space vehicles has decreased by an order of magnitude. And you see that for some of the big players in the high-density communication cluster, industry. What used to be years is now months. And this is driving down lead times, both for qualification and manufacturing across the entire supply chain. 5 years ago, 12-month lead time was fine for space qualified electronics. That was acceptable back then. Today, you have customers asking for like 12 weeks. I guess third, the number of commercial and military satellites being inserted into orbit is increasing significantly. Think about it. 20 years ago, you might have a couple hundred satellites launched per year, and many of them were military. With the advent of, the high-density communication constellations coming up, next year, guys, we could see a couple hundred satellites being launched every month, right? And so this is decreasing a huge demand for RF space parts. We estimate between 8 and 10 times what it was a couple years ago.
So from a system level, what do you see as the greatest challenges to insert new technology into space?
Well, right now, radiation susceptibility, things like power efficiency, and then I guess the thermal management still remain at the top of the list of concerns. We are seeing needs for greater integration in packages or even modules. And as in most emerging markets, we're starting to see increased pressure on cost and schedule, which challenge all of us. While the radiation requirements in space, I guess at least for maybe the on-orbit space vehicles, are evolving, high reliability semiconductors are still required, probably for all except either the shortest or the lowest value missions. In RF and microwave, though, we have some advantages in that our processes, at least some of the new evolving ones, are based on gallium arsenide or gallium nitride, and that provides a pretty strong foundation for radiation tolerance, for products like amplifiers or switches. And hopefully, and I think we've seen it already demonstrated, this reduces the lead time and actually mitigates some of the radiation concerns. Still though, probably the greatest challenge for the on-orbit assets is the power budget and managing the thermal issues, even more so in things like RF and microwave. A low Earth orbit satellite, guys, spends about half its time eclipsed by the Earth, so it's in the shadow. And as you guys can imagine, while drawing on battery power, the bird itself may not only have to power its systems and payloads, but occasionally even has to turn on electric heaters to maintain temperature. This can be a big challenge for a system that goes around the Earth once every 90 minutes. Conversely, I think, as you guys know, space has no convection, no conduction of heat. And so the management of thermal dissipation becomes a real key challenge. Requires really careful planning to avoid compromising things like duty cycles and actually can hinder the operation of some of the critical payloads. Power and heat create a challenge when using some of the newer RF and microwave semiconductors that I think we're starting to see success in, like terrestrial applications. 5G is a good example. Some of the other high power communications are good. But in many cases, the big challenge we're looking at is that it's difficult, if just not downright impossible, to lift a terrestrial phased array design, for example, and just deploy it into space, primarily because of the aforementioned like thermal constraints.
So what changes are you and ADI having to make to address the latest changes in the space market?
Great question. So first off, Analog Devices, we've created a brand new product line focused on commercial space. What we're doing is we provide a commercial space high or commercial space low qualification along with the manufacturing flows that go with it. And these are specifically targeted to the next generation of the satellites. Important to note that we aren't, these new commercial space flows, especially commercial space high, doesn't just serve the LEO orbits. This is actually usable and has had some adoption all the way through the geostationary orbits. So a wide availability and ability to mitigate some radiation concerns across the designs. These commercial space flows are also envisioned to provide customers, with plastic packaged components up to probably 100 kilorad or so. And we're going to add things that you normally would see in some space products like, radiation lot acceptance test, some outgas evaluation. We'll extend the temperature range. We'll mitigate concerns about tin whiskers. We'll do some pedigree tracking. And then we can also add some additional high reliability features that you normally just expect depending on the flows. And these flows are not just for components. We could actually probably add these to things like system and package and modules as well. It's important to note, though, guys, that we're not abandoning our legacy QMLV and Class K family of products, though. So I guess the company of these commercial space flows is that we need to reduce the space product lead times, both for qualification and to actually deliver products. As I mentioned before, customers need to get the latest products on orbit quickly in order to compete. And, we at Analog Devices are changing to meet that need. Now, much akin, I think, to our defense customers, our space customers are asking us to do more integration and provide more of the RF and microwave design so they can get on orbit faster. Very much aligned with what we're seeing in the rest of the aerospace and defense industry. Analog Devices is, we're evaluating presently a number of solutions that pull most of the RF and microwave design into either one integrated package, a set of fewer integrated packages, some complementary designs where we're with partners, or actually modules which can be qualified for space, or important to note, some other radiation sensitive applications, some of those in healthcare, some in the missile munitions business. Finally, something I think is really exciting, and I think it deserves note, is we're expanding our ecosystem. So what we're doing is expanding this ecosystem we have to include more partner companies who can speed building our catalog, but probably of equal or greater importance, those guys that we can actually enable with our technology to serve customers in the space industry faster with their own specific applications.
So you've alluded to some of the new technologies going into space that rely on RF microwave. And I'm thinking, for example, payloads that are using active arrays for, let's say, broadband internet access. What advances are needed to support these on-orbit space vehicles?
Well, I think the industry, if you look at the terrestrial solutions we have, we're well positioned as far as technology. Example for us is we've got, our Hittite portfolio of very strong RF microwave components. You pair that with the LDOs from Linear Technology and the power parts, and then everything joined back to the legacy Analog Devices portfolio. It gives us a leadership position on RF and microwave, but more importantly, you see that we almost have a complete solution. Our challenges revolve around actually getting that correct solution qualified to the right radiation tolerances into the market to enable those customers to compete. And that's becoming the biggest challenge right now. You have a couple solutions that, I always use 5G as an example. 5G has some great solutions, but they also have the ability to provide a lot more cooling. They also have the ability to actually consume a lot more power than you would in a space application. So a good example is like presently we have a beamforming integrated circuit, or BFIC. It excels in power, size, and thermal compared to a lot of those competing designs. What we need to do now is work to get that type of product into space in the next 12 months. We are releasing next year our first space-grade high-speed ADCs and DACs. That's going to bring some of the modern products to the space market shortly after the commercial versions were released. We're building out a set of power portfolio products that actually will support the RF and microwave developments in space as well. I think something that you brought up, some of the electronic steered arrays, and maybe two things that I'm going to kind of maybe take a kind of a different slant on is, though not directly related to RF and microwave, one of the products that we really see needed in space is a MEMS IMU solution, especially in light of the advances in the electronic steered arrays. They're very highly utilized in terrestrial applications. We need to still be able to start moving those so that when you steer beams, you have greater accuracy, as opposed to relying on either a star tracker or an onboard central IMU to do that. I think some of the challenges, many legacy space grade IMUs are really, really expensive. They cost sometimes half of the entire electronic component BOM. And honestly, guys, they exceed good enough by a huge margin. I think the industry needs to qualify more of the mid-range IMUs into the space market to go and complement some of our good RF and microwave phased array type stuff for communications. Kind of the same goes for other things like reaction wheels and torque rods and other things that go in the satellites. I think also not unique to space, but as we move up higher in frequencies and geometry, you see the auctions to clear spectrum and actually move the space spectrum higher up in frequency. Geometry and size constraints on the antenna are driving huge reduction of activities, and initiatives like antenna on package. I think we need to get those and that technology on orbit very quickly in the next few years. I guess another concern, probably familiar to those in the terrestrial market, which is interference and blockers. It's going to be a challenge across the entire industry. Historically, there has not been a lot of on-orbit to ground communication outside of the military and very specific applications like Iridium, where it's actually two-way or basically internet from ground to satellite. With plans for thousands of satellites on orbit, sharing the same spectrum, this is where a lot of the 5G guys will understand this. There's going to be a need for a really robust system because you're going to have plenty of blockers and plenty of interference. So we have to develop systems both on the ground and on orbit that can function through a lot of these issues related to high utilization. And then I think the other one, I speak a lot about this, but space is unique in power budgeting. And the RF and microwave designs are mature and proven for probably most parts of the allocated spectrum. But behind the scenes, we need to actually continue to work to increase the efficiencies of power, especially battery management systems, or what is sometimes called BMS. Many satellite manufacturers, they're moving towards these lithium-based technologies for batteries. It's very similar to what you see used in automotive electrification. And to support some of the growing needs for the power to power the RF systems, we really need to move these systems, which are already proven in automobiles, into satellites to be more efficient, reduce the power loss and get rid of some of the inefficiencies due to either charge state or charge management. And I think, some of the new commercial space flows, it's going to accelerate the qualification and getting these technologies into the customer's hands.
So you mentioned beamforming integrated circuits. Can you tell us a bit more about that family of products and what challenges they solve?
So I think this is a really exciting time, right? You look at what they're doing in 5G beamforming systems, right? And we at Analog Devices were leaders in the enabling technology for a lot of the 5G and even terrestrial things like radar and other military communication systems that are based on electronically steered arrays. We have a strong catalog of beamforming products, ranging from everything like you may have seen the ADVM, the 4801, up to our beamforming integrated circuit, or BFIC, which is, we have an X-band and K-band 80AR 1000, which is our most recent release. This can be paired very nicely with the commercial space flow, and it allows this proven technology to fly in orbit very quickly. I think, as I mentioned before, we expect to have our first basically full BFIC or beamformer IC on orbit in about 12 months. The other thing about the BFIC is that it's great advantage in that it's primarily based on an analog time delay architecture, so it minimizes the number of digitizers and FPGAs required to generate and steer beams. Those two are, while great technologies, also, again, have a huge penalty when it comes to thermal and power. Aside from mitigating heat and power concerns, the design also may have less digital susceptibility to radiation because of the way it's designed. It's much more on the analog RF side. Each integrated component supports 4 channels. And of course, as I mentioned before, it could be paired with one of our multiple channel. We have a low noise amplifier and also a high power amplifier that also can be qualified to these commercial space standards. So I think it goes a long way to, solving some of the problems and some of the concerns about, AESA type arrays up in space.
So we hear a lot about the commercial space model, perhaps not as much about military satellites. What changes do you see in the military's approach in the coming years?
So I think, if you look, Gary, over the past few weeks, we've seen numerous indications that the government is not only going to consider commercial space models, but they're going to fully embrace it. There's been 4 or 5 awards announced and some research projects announced just over the last week that really gives credence to that belief. The military has been exploring ways to move technology into space faster for over 20 years. About 20 years ago, a program called Operational Responsive Space, ORS, was created to drive new technologies that put the assets on orbit in months as opposed to years. And extensive research has been done on the use of commercial products and spaceborne applications by the military for a very, very long time. I believe the driving factor, by the way, guys, is not so much cost. It's important. Cost is important. But I think really what they want is the ability to get the latest technologies in orbit quickly to respond to some of the new emerging threats that they're seeing out there. The new Space Force, it's a welcome addition. I think it's going to drive the next generation of military satellites. Something that's really, I think, exciting is they're already contracting with what a lot of the government contracting calls non-traditional companies to acquire hardware, services, and bandwidth. I would expect that to further drive, towards a commercial space model, probably in the next 3 to 5 years.
Sean, thanks for joining us today, sharing your insight into the transitions that are taking place in the space industry and how Analog Devices is moving to intercept those. We're clearly witnessing a new generation of launch vehicles, satellite technology, and industry government collaboration, and it's a fun time to be part of it.